Hey fellow nerds! In this video, we're going to continue our journey with elementary signals used in signals and systems. Today we'll learn unit step function, rectangular function, signum function, and unit ramp function. Let us start with continuous time unit step function. It is denoted as u of t. And u of t is 0 for all t less than 0 and it is 1 for all t greater than or equal to 0. So on a graph it can be shown like this. It is 0 at first and then at 0 it becomes 1 and continues to be 1. Let us see how it is related with a unit impulse function. U of t can be defined as integral from minus infinity to t delta of t dt. To analyze this equation, we have a graph of delta of t over here. Assume that I'm taking a t over here and I want to find out my u of t at that point. According to this equation, I have to start integrating from minus infinity to this point. But if I integrate from minus infinity to this point, you can see there is no value in between and I will get 0. In fact, up to 0, I will get the same. But at 0, suddenly I have 1 over here. When I integrate, I'll get the area under this graph, and area under the graph for delta of t is 1. So suddenly at 0, I will get 1 like this. Then what happens? Let's say I took some time here and I'm integrating from here to here. So again, the only thing that exists in between is one impulse over here which gives me 1. So it doesn't matter where I take t after that, I will always get 1. So we can confirm the relation is true. U of t is just integral from minus infinity to t delta of t dt. And obviously, if u of t is the integration of delta of t will be the derivation of u of t. So delta of t is d by dt of u of t. You can see that over here. From minus infinity to here, there is no change. So derivation which gives us the slope is 0. Here also, slope is not changing. So derivation is 0. But here, there is a sudden change from 0 to 1. So at 0, we get an impulse like this. Let's learn some of the properties of continuous time unit step function, the first one being amplitude scaling. Mathematically, we can define it like this. If you take k u of t, instead of 1 for u of t, you will get k for all t that is greater than or equal to 0, and then you will get 0 where t is less than 0. That is all the values have been scaled by k. On a graph, here we have u of t where this magnitude is 1. If you want k u of t, you will get something like this. And this value is going to be k. The next property is time shifting. So over here we have u of t, which has the sudden change happening at t equal to 0. Now, if we take u of t minus t naught, the whole signal will move t naught units towards the right. So it will look like this. The sudden change is now happening at plus t naught. If you take u of t plus t naught, then you will get the sudden change at minus t naught because now your signal has moved t naught units towards the left. Mathematically, this is how you show it. U of t minus t naught, it gives you 1 if t is greater than or equal to t naught, and it gives you 0 if t is less than t naught. On the other hand, u of t plus t naught will give you 1 if t is greater than or equal to minus t naught, and 0 if t is less than minus t naught as shown in the second case. Let's move on to the next property, which is time scaling. Let's take an example to understand this. So we know how u of t is. Let's take u of 2t. When I take t equals 0, I'll get u of 2 times 0, that is u of 0. When I take t equals 1, I'll get u of 2 times 1, u of 2, which is again 1. Because all positive values of t, we are getting 1 for a unit step function. Even if I take t equals 2, 3, 4, etc., I am getting u of 4, u of 6, u of 8, etc. but we know if whatever is inside the bracket is greater than 0, we're getting 1. So all these points I'll still get 1. Even after taking u of 2t, I'm still getting everything after 0 is 1. How about something that is negative? Let's take t equals minus 1. Then I'll get u of minus 2, but u of minus 2 is 0. Then if I take t equals minus 2, I'll get u of minus 4, that is 0. So it doesn't matter if you're taking u of 2t, you're still getting 1 for all the positive values and 0 for all the negative values. Which means if you try to plot u of 2t, you will get the very same graph like this. So mathematically, we can write u of at is equal to u of t. But the question here is, what if a is less than 0? What if a is negative? Let's take a negative value for a now. I will take u of minus 2t. So at t equal to 0, just like before, I'll get u of minus 2 into 0, that is u of 0, which is equal to 1. For t equal to 1, I will get u of minus 2, which is 0. For t equal to 2, I'll get u of minus 4, which is 0. So just like this, for every value that is greater than 0, I'm getting 0 now. What if I'm taking t equals minus 1, for example? Then I'll get u of minus 2 into minus 2, which is plus 2, and u of 2 is supposed to be 1. So what we can see here is that if a is negative, then the graph will be mirrored about the y-axis. So u of minus 2t will look like this. It will be 0 for t greater than 0, but 1 for t less than 0. So we have to include that also in the equation. So we can write u of at is going to be equal to u of t itself if a is greater than 0. It is going to be u of minus t, that is time reversed u of t, if a is less than 0. The next property is time reversal, which we should have learned before time scaling. But it's all right, time reversal is not alien to you at all. We have done it before. So if u of t looks like this, u of minus t will be the mirror image about the y-axis. So it kind of looks like this. How do we write this mathematically? We can write u of minus t is going to be 1 if t is less than or equal to 0, and it is going to be 0 if t is greater than 0. Here, this is what we call a right-sided signal because it only has value that is not equal to 0 on the right side of t equal to 0. And this is what we call a left-sided signal because obviously it only has value on the left side. Now let's try to do a mixed operation. We have u of at plus b. First of all, obviously we have to write it in the standard form. So u of a into t plus b by a. A will be corresponding to time scaling, b by a will be corresponding to time shifting. In time scaling, we saw that when a is greater than 0, we get u of t, and when a is less than 0, we get u of minus t. So here also we'll have to take both cases because we don't know the sign of a, which is the scaling factor. And then we have t plus b by a, which obviously shows us the point where the transition happens from 0 to 1 is minus b by a. So let's mark minus b by a on both graphs. If a is greater than 0, my signal is going to be right-sided and the transition is going to happen at minus b by a. So we'll get something like this. On the other hand, if a is less than 0, I'm going to get a left-sided signal and the transition is going to happen at minus b by a. So it looks like this. Nothing happened to the magnitude, so it is still 1. The next and final property we are dealing with now is sampling property. Consider x of t, which is a random signal like this, and then we have u of t, which transitions at 0. We are multiplying both of these together. So over here we have 0, multiplying it with whatever, we'll get 0 here. Over here we have 1, multiplying it with x of t, we'll get x of t. To show the graph properly, I'll just copy and paste this. This is how it looks like, but on the left side, we won't have this. We'll just have 0. On the right side, we have whatever is x of t. Mathematically, we can write it like this. X of t multiplied by u of t will be equal to x of t itself if t is greater than or equal to 0, and it will be 0 if t is less than 0. I have a question. What if I want to sample my signal from some other point? I want all the points from here towards the left. Then what do I do? Obviously, I will take a time shifted unit step function, something that transitions over here, then I'll get it. We have done similar exercises before, so I'm sure you're familiar with it. Let's go on and solve some problems. First, we have to plot x of t, and x of t is 1 plus 2u of t. We know u of t is 1 for t greater than or equal to 0 and 0 for t less than 0. But if I take 2u of t, that is amplitude scaling, amplitude will be multiplied by 2 everywhere. So at 1, I get 2, at 0, I still get 0. Then in our function, I have to add 1 everywhere. So 1 plus, I add 1 to 2, so that becomes 3. I add 1 to 0, so that becomes, when t is less than 0, we get 1. And when t equal to 0, there is a sudden transition from 1 to 3. And then it continues to be 3. Let us solve another question. Here we have to plot x of t, which is u of sine t. To understand how this can be done, let's bring back u of t for a moment. U of t is 1 if t is greater than or equal to 0, and it is 0 if t is less than or equal to 0. In other words, we can say that u of t is 1 if whatever is inside the bracket is greater than or equal to 0, and it is 0 if whatever is inside the bracket is less than or equal to 0. Using that logic, we can write u of sine t is going to be 1 if sine t is greater than or equal to 0, and it is going to be 0 if sine t is less than 0. Now we can pretty easily plot u of sine t. I have already drawn a sine function over here, and you can see this is a positive half cycle, negative half cycle, positive, negative. In the positive half cycle, sine t has positive values. So u of sine t will have 1. In the negative half cycle, sine t is negative, so u of sine t will be 0. The graph of u of sine t will look like this. Now let's learn a very common function that we use in signals and systems. It is called rectangular function. On a graph, it is shown over here. We have 1 from minus 1 by 2 to 1 by 2. Everywhere else, we have 0. Mathematically, we can write it like this. Rectangular function of t, or you can write it like this. Rectangular function of t. This will be 1 if t is between minus 1 by 2 and 1 by 2. So we can write 1 if modulus of t is less than 1 by 2. And 0 if modulus of t is greater than 1 by 2. Now, why did I write it under unit step function? It is because they have a very close relation. There is another interesting way of defining a rectangular function. You can write it this way. Rectangular function of t is equal to u of t plus 1 by 2 minus u of t minus 1 by 2. Let's verify this. What is u of t plus 1 by 2? It is u of t shifted 1 by 2 units towards left. That is, it will look like this: 0 until minus 1 by 2 and then 1 until infinity. Then we have u of t minus 1 by 2. This is u of t shifted half units towards the right. So it will be 0 until 1 by 2 and then it goes on like that. So we have this signal u of t plus 1 by 2, from which we are deleting this much. So if that is gone, what is left is a rectangular function. Let's move on to another common function that we will encounter in signals and systems, that is Signum function. Graphically, this is how it looks like. For every t that is negative, it's going to be minus 1. There is a sudden shift at 0. When t is greater than 0, it is plus 1. Mathematically, we can write it like this: Signum function of t, it's 1 for t greater than 0, it is 0 for t equal to 0, and it is minus 1 when t is less than 0. Another way of writing this is, I can just write Signum function of t is t divided by mod t if t is greater than 0 or t is less than 0, and 0 if t is equal to 0. Let's verify this. I am taking a value that is greater than 0. I will take 2. Then t divided by mod t will be 2 divided by mod of 2. I get 1. Rightfully so. For a value that is greater than 0, I am supposed to get 1 only. Now I'll take a minus 2. T divided by mod t minus 2 divided by mod of minus 2. That is minus 2 divided by 2. This is minus 1. Exactly what I was expecting. Again, Signum function can also be written as a function of u of t. Signum of t is nothing but 2u of t minus 1. How is that possible? We know when t is less than 0, u of t is 0. So 2u of t is also 0. So you will just get minus 1, which is correct. When t is greater than 0, u of t is 1. 2u of t is 2. 2 minus 1, you will get plus 1. So that is also correct. Let us now solve a question. Whenever we have a problem to solve, it will be better if you pause the video and try to solve it yourself first and then check if it is correct or not. Here the question is, we have to plot x of t. X of t is rectangular function of t by 4 minus signum of t minus 1. We will plot them separately and then take the difference. So this is not rectangular function of t, it is rectangular function of t by 4. So what is happening to a rectangular function is time scaling. And the scaling factor is 1 by 4, which is less than 1. So it is going to expand. Originally, rectangular function of t was from minus 1 by 2 to 1 by 2. Now it will be from minus 1 by 2 multiplied by 4 to 1 by 2 multiplied by 4, which is minus 2 to 2. So we can write it is going to be 1 for minus 2 less than or equal to 2 less than or equal to 2, and it is going to be 0 everywhere else. Similarly, what is happening to the Signum function here is time shifting. We have t minus 1, which means it is going to shift 1 units towards the right. Mathematically, we get signum of t minus 1 is going to be minus 1 if t less than 1. The transition is now happening at plus 1. And plus 1 if t is greater than 1. Let's plot them one by one. I will mark minus 2 here and plus 2 here. The rectangular function will be 0, 1, again 0. For Signum function, let me mark minus 2, minus 1, 1 and plus 2. It is -1 until t is equal to 1. Then there is a sudden shift, after which it becomes 1. Now let us take the difference. Until 2, here we just have 0. Here we have -1. So 0 minus -1 is 1. Before that, let's mark -2, -1, 1, and 2. Until -2, we have +1. After that, here we have +1. Here we have -1. So 1 minus -1, and it's actually true until t equals 1. So it will be like this. After 1, here we still have 1, but here also we have 1. So from 1 to 2 we have 0. And then after 2 this is 0, this is 1. So 0 minus 1 we get -1. That's about it. Let's solve the next question. We have x of t, which is signum of cos t. We have plotted u of cos t before. We already know signum of t is -1 if t is less than 0 and 1 if t is greater than 0. Or in other words, we can say it is -1 if whatever is inside the bracket is less than 0. It is 1 if whatever is inside the bracket is greater than 0. So if whatever is inside the bracket is cos t, then it will be 1 if cos t is positive, it will be -1 if cos t is negative. If cos t is 0, signum function will be 0. Let's mathematically write it. Signum of cos t, it will be -1 if cos t is less than 0. It will be 0 if cos t is equal to 0, and it will be 1 if cos t is greater than 0. Over here, I have already plotted cos t, and you can see there are positive half cycles and negative half cycles. In the positive half cycles, we will get +1 for the signum function. In the negative half cycles, the signum function will become -1. So it will look like this. Let us now move on to discrete time unit step sequence. It is denoted as u of n with square brackets, of course. Mathematically, it is defined like this. U of n is 0. If n is less than 0, it is 1 if n is greater than or equal to 0. Graphically, it can be shown like this. Till -1, we have 0. After 0, we have 1 forever. It can also be written as a sequence like this. We have 0 until -1, and after that we get 1 forever. This is obtained by sampling u of t. Let's do some properties. The first property is amplitude scaling, which is pretty easy since u of n has 1 after 0. K u of n will have k after 0. Mathematically, we can write k u of n is going to be equal to k if n is greater than or equal to 0, and 0 if n is less than 0. The next property is time shifting. If we are taking u of n minus n naught, our signal will shift n naught units towards the right. So now up until n naught minus 1, we will have 0 everywhere. From n naught, we have 1. Similarly, u of n plus n naught is u of n shifted n naught units towards the left. Up until minus n naught minus 1, we have 0. After that, we start getting 1. Mathematically, we'll write it like this. U of n minus n naught will be 1 as long as n is greater than or equal to n naught, and 0 if n is less than n naught. Similarly, u of n plus n naught, this will be 1 as long as n is greater than or equal to minus n naught, and 0 if n is less than minus n naught. Our next property is time reversal. U of n looks like this. 0 until -1, and from 0 we have 1. On the other side, if you take u of minus n, you will have 0 from 1 to infinity, and from -infinity to 0 you have 1. Let's write the mathematical definition. 1 if n is less than or equal to 0, and it is 0 if n is greater than 0. One thing you can notice here is that for n equal to 0, we have 1 in both these functions. Our next property is time scaling. Let's move on to the next property, which is time scaling. Time scaling in discrete time unit step sequence is very similar to what we did in continuous time unit step sequence. Time scaling in discrete time unit step sequence is very similar to what we did in continuous time unit step function. Before that, we use the word sequence when it is discrete and function when it is continuous. It's not wrong if you say discrete time unit step function, it is just a conventional way of differentiating them. So, in continuous time unit step function, we saw if you take u of at, it doesn't really change anything. If a is greater than 0, you still get u of n. But if a is less than, sorry, 0, but if a is less than 0, you get u of minus n, that is a left sided signal. The same thing happens here also. We have u of n, which starts having 1 from 0 to infinity. If you take u of 2n, nothing will change because 2 is a value greater than positive number, so you will still get 1 from 0 to infinity. But if you take u of minus 2n, then you will get a left-handed signal from minus infinity to 1. From minus infinity to 0, you will have 1. After that, you will get 0. So u of an can be written as u of n itself if a is greater than 0, and it can be written as u of minus n if a is less than 0. I should write a greater than or equal to 0 because 0 is also included in both cases, because 0 is also to be included. Now the question is, am I telling you that time scaling has literally no effect in the sequence and previously in the function, other than that if it is negative, it becomes mirrored? Actually, though it is not visually sensible, there is something else that is happening when you apply time scaling. This is applicable to the continuous time function also. That is, if mode A is greater than 1, then compression will happen. Usually, when we take x of 80, that is time scaling, what happens is if A is greater than 1, our signal compresses. If A is less than 1, our signal expands. But over here, the thing is, it is already from 0 to infinity. So even if it compresses or expands in between, we won't be visually able to see it. But it is happening. But it is actually but it is happening. If mode A is greater than 1, compression will happen. We won't be able to see it on the graph, but the transition occurs more rapidly. Similarly, if mode A is between 0 and 1, then expansion happens. Though you won't be able to see it, the transition between values occur more slowly. Now let's do a mixed operation. We have u of an plus b. First, we'll write it in standard form, u of a into n plus b by a. Now a will do the time scaling, b by a will do the time shifting. Let's take the first case where b by a is an integer. There are two more cases depending on the value of a as well. In time scaling, if a is greater than 0, we get a right sided signal. If a is less than 0, we get a left sided signal. So I have taken both options. Here we get right sided, here we'll get left sided. Also n plus b by a. So the point where the transition happens will be minus b by a, and it is an integer. So let's mark minus b by a on both graphs. So transition happens at minus b by a, and here we want a right sided signal. So at every point right to minus b by a, we'll get 1. And at every point towards the left of minus b by a will be 0. On the other hand, here we want a left-sided signal. Transition is at b by a. So towards the left of b by a, we'll get 1. And towards the right of minus b by a, we get 0. Let's move on to the next case where b by a is not an integer. Let's say our minus b by a was somewhere over here between two integers. Now u of n, that is a discrete time unit step sequence, can only have values when n is an integer. So at minus b by a, we cannot have any value. So what we do here is, in the first case when a is greater than 0 and we want a right-sided signal, we take the very next integer towards the right, which is over here. So from here we give 1 and we get our signal. On the other hand, if a is less than 0 and we want a left-sided signal, we take the very next integer on the left side, that's over here, and from there we start giving 1. Let's go to the next property, which is sampling property. We have an x of n, which is a random signal, and we have u of n, and then we'll take x of n multiplied by u of n. Obviously, we have 0 at all these points. So when you multiply it with the values of x of n, you'll get 0. And from 0 to the right side, we have 1. So when you multiply it with x of n, you get whatever is the value of x of n there. So until minus 1, we get 0. After minus 1, we get x of n. Let's write it mathematically. X of n multiplied with u of n will be x of n if n is greater than or equal to 0, and it is 0 if n is less than 0. Let's now find out the relationship of a discrete time unit step sequence with an discrete time impulse function. Very interestingly, delta of n can be written as u of n minus u of n minus 1. How? U of n has 1 at all these places. U of n minus 1 has 1 at all these places because it has been shifted 1 units towards right. So when you subtract u of n minus 1 from n, these will be cancelled. All of these will be cancelled. The only thing left is at n equal to 0, which means we get delta of n. If you want to get the opposite, all we have to do is summation from k equal to 0 to infinity delta of n minus k. How? Let's try giving values to k. When k equal to 0, you get delta of n minus 0, delta of n. Plus, when k is 1, you get delta of n minus 1. When k is 2, you get delta of n minus 2. So basically, you have an impulse at 0, you have an impulse at 1, you have 1 at 2, and then it goes on like that, which technically just gave you u of n. Now let's move on to some very interesting results. First one says u of n plus u of minus n is 1 plus delta of n. I have u of n here. It has 1 from 0 to infinity. I have u of minus 1 here. It has 0 from minus infinity to 0. If I add them, till minus 1, I have 0 here, I have 1 here. So I'll get 1 everywhere. From 1 to infinity, I have 0 here, I have 1 here. So when I add them, I'll get 1. Only at 0, I have 1 at both places, so I will get 2. So it is equivalent to having 1 everywhere, but an extra 1 at 0. That is, it will be equivalent to taking 1 plus delta of n. The next result is u of n multiplied with u of minus n is also delta of n. We can see that also in the graph. We have 0 everywhere, you multiply it with these, you get 0. You have 0 everywhere here, you multiply it with this, you will get 0. Only at 0 you have 1 and 1. So when you multiply them, there will be value at 0 only, and we call that delta of n. The next thing says u of n into u of minus n minus 1 is 0. How come that is true? We know u of n has value from 0 to infinity, including 0. How about u of minus n minus 1? To plot u of minus n minus 1, first we have to write it in the standard form. That is u of, take minus 1 out, n plus 1. Minus 1 does the time reversal or the time scaling, plus 1 does the time shifting. So since this is minus, we'll get time reversal, that is a left-sided signal like this, but then there is a shifting as well, plus 1. So it has to shift 1 unit towards the left. So our signal will start at minus 1. Let's remove this, make it 0. And this is now u of minus n minus 1. Now if we multiply them, we have 0 until minus 1. We have 1 here, so we'll get 0. From 0 we have 0 here. From 0 we have 1 here. When multiplied, we'll get 0. So yes, u of n multiplied with u of minus n minus 1 is equal to 0. A very interesting observation that we can make over here, which is very important for you to be studying signals and systems, is that when you say u of t and u of minus t in the continuous domain, the corresponding sequences in discrete time domain is u of n and u of minus n minus 1, not u of minus n, because u of minus n overlaps with u of n at 0. They both have 1 at 0. If you look at these two, they are the opposites. This one has value from 0 to infinity. This one has value from minus 1 to infinity. They are not overlapping. So, u of minus n minus 1 is analogous to u of minus t. The next one is u of n plus u of minus n minus 1 is 1. It is true because we have 1 over here, we have 0 over here, we add them, we get 1. We have 1s over here, we have zeros correspondingly, adding them you will get 1 everywhere. So u of n plus u of minus n minus 1 is 1. Let's now solve some problems. The first question is to plot x of n, which is u of 0.5 n minus 2. First, let's write this in standard form. U of, we have to take 0.5 out, then it will be n minus 2 by 0.5 is 4. Two things we can see is the scaling factor 0.5 is positive and the time shifting factor is an integer. Since this is positive, we'll get a right-sided signal. Since this is an integer, the transition will happen at n equals 4. So our graph will look like this. The next question is to plot x of n, which is u of minus 2n plus 3. Again, let's write it in standard form. U of, take minus 2 out, n minus 3 by 2. Here the scaling factor is minus 2, it is negative. And time shifting is given by minus 3 by 2, which is not an integer. Since this is negative, we should have a left-sided signal. And since here we have 3 by 2, which is 1.5, it should start from the integer that is next to 1.5. 1.5 will be around here, and since we're taking a left-sided signal, we'll have to start from 1. Our graph is going to look like this. Next question is to plot x of it, that is u of 2n plus 3. In standard form, this is going to be u of 2 into n plus 3 by 2. 2 is positive, so we get a right-sided signal, and 3 by 2 is not an integer. Since 2 is positive, we need a right-sided signal, and since we have plus 3 by 2 here, it should start from an integer next to minus 3 by 2. Minus 3 by 2 will be somewhere around here, and for a right-sided signal, we should start with minus 1. Let's now move on to our next signal, continuous time unit ramp function. It is denoted as R of t. Mathematically, it is defined like this. R of t is t for all t greater than or equal to 0, and 0 for all t less than 0. Since it only has value when t is greater than or equal to 0, we can write it like this also. R of t is t u of t. Graphically, it can be shown like this. Till 0 we have 0. After that we have a line which has a slope 1. The first property we are going to learn is amplitude scaling. Kr of t is going to be k multiplied by t if t is greater than or equal to 0, and still going to be 0 if t is less than 0. Let's take different cases. If k is greater than 1, for example 2, we get 2r of t. So every value here will be multiplied by 2. Its slope becomes 2. So kr of t when k is greater than 1 will look like this. Its slope is going to be k. If k is a positive number that is less than 1, for example, let's say we took 0.5 r of t. What happens is every value will be halved, so the slope will also be halved. Over here, the graph will look like this, and the slope will be less than 1 but still positive. Now consider k is less than minus 1. For example, we'll take minus 2r of t. So every value of r of t will be multiplied by minus 2. At t equal to 0, we get minus 2r of 0. R of 0 is 0, so we get 0. At t equal to 1, we get minus 2r of 1. R of 1 is 1, so we get minus 2. So along with doubling the amplitude, it is also negative now. That means our graph will look like this, and its slope is going to be minus k. Now finally, if k is a negative number that is greater than minus 1, we get a similar graph, except the slope is going to be lesser now. The next property is time shifting. In r of t, the gradual increase starts at 0. If I take r of t minus t naught, it starts at t naught. And if I take r of t plus t naught, it starts at minus t naught. Mathematically, we can write it like this. R of t minus t naught is going to be equal to t minus t naught if t is greater than or equal to t naught, and it's going to be 0 if t is less than t naught. Similarly, r of t plus t naught is going to be t plus t naught if t is greater than or equal to minus t naught, and it's going to be 0 if t is less than minus t naught. The next property is time scaling. That is, we'll take r of kt. We'll take different cases, first one being k greater than 1. Let's take an example, r of 2t. Then at t equal to 0, I get r of 0. At t equal to 1, I get r of 2. At t equal to 2, I'm getting r of 4. So technically, every value is getting multiplied by 2, which means our slope will increase by k. Graph will look like this. In the next case, we are taking 0 less than k less than 1. Let's take an example, r of 0.5 t. If I take t equal to 0, I still get r of 0. If I take t equal to 1, I'm only getting r of 0.5. If I take 2, that's when I actually get r of 1. So it's a bit slow. That means the slope will decrease. Graphically, we can show it like this. The slope will be less than 1. Moving on to the next case, we have k is less than minus 1. Let's take an example, r of minus 2t. At t equal to 0, I will still get r of 0. At t equal to 1, I will get r of minus 2. At t equal to 2, I get r of minus 4. But we know r of t only has values when t is positive. R of minus 2 is 0, r of minus 4 is 0. So if you keep taking positive values for t, you will keep getting 0, which means there is nothing on the positive side of the time axis. On the other hand, if you take t equals minus 1, you will get r of minus 2 into minus 1, 2. If you take t equals minus 2, you will get r of 4. We know r of t is t, so r of 2 will be 2 and this will be 4. So at t equals minus 1, you will get 2. At t equals minus 2, you will get 4. That means our graph is going to look like this towards the left side, and the magnitude of the slope is greater than k. Slope is still negative. The next case is when k is between minus 1 and 0. Taking an example, r of minus 0.5 t. At t equal to 0, we get r of 0, which is 0. At t equals 1, we're getting r of minus 0.5, which is 0. Similarly, if you take any positive value, you will get 0 only, just like this. Let's take a negative value now. If t is equal to minus 1, you get r of minus 0.5 multiplied by minus 1, r of 0.5, which is 0.5. If you take t equals minus 2, you get r of 1, that is 1. So it will look like this graph, but it will be slower, which means its slope is going to be lesser. Mathematically, let's write it down. For k is greater than 0, r of kt will be equal to kt if t is greater than or equal to 0 and 0 if t is less than 0. That is what we saw in the first two cases. For k being less than 0, r of kt will be equal to kt if t is less than or equal to 0 and 0 if t is greater than 0. That is what we can see over here. The next property I've taken is time reversal. In time reversal, whatever is on the left will now become on the right, whatever is on the right will now become on the left. So mathematically, it can be written like this. R of minus t will be minus t if t is less than or equal to 0 and 0 if t is greater than 0. Now let's understand the relationship between continuous time unit ramp function and continuous time unit step function. R of t can be written as integral from 0 to t u of t dt, and u of t can be written as d by dt of r of t. It's obvious from the graphs itself. What you have here is a line with slope 1. If you differentiate it, what you get will be the slope which is 1. So that means you should get 1 everywhere, exactly what you're getting in u of t. So u of t is d by dt of r of t. And consequently, r of t will be integral 0 to t of u of t. Let's solve a problem now. We have to plot x of t, which is r of t minus r of t minus 1. We know r of t is going to be 0 if t is less than 0. It is going to be t for all t that is greater than or equal to 0, but let us split it for now. Let's write it is t for 0 less than t less than 1. It is again t for t greater than 1. The next one is r of t minus 1, which is a time shifted version of r of t. So r of t minus 1 will be 0 for all t less than 0. This is also going to be 0 for 0 less than t less than 1, because here the gradual increase only starts at 1. After that, it's going to be t minus 1 when t is greater than 1. What we need is r of t minus r of t minus 1. When t is less than 0, this is 0, this is also 0. So we get 0 in our graph. So x of t is going to be 0 itself when t is less than 0. When t is between 0 and 1, r of t is t and r of t minus 1 is 0. So t minus 0, we have to get t. So it is t when 0 is less than t is less than 1. When t is greater than 1, here we have t. When t is greater than 1, here we have t minus 1. So we'll get t minus t plus 1. That is 1 when t is greater than 1. Now we can plot this on a graph. Until 0, we have 0. Until 1, we have t. After that, we just have 1. Let us now learn discrete time unit ramp sequence. It is defined as r of n with square brackets. Mathematically, it is defined like this. R of n is n when n is greater than or equal to 0, and it is 0 when n less than 0. But we know in discrete time sequences, there are values only when n is an integer. So the integer right before 0 is minus 1 only. So we can write it this way also. It is 0 when n is less than or equal to minus 1. Graphically, it will look like this. Till 0, we have 0. After that, we just have the value that is equal to value of n. At n equal to 1, we have 1. At n equal to 2, we have 2. At n equal to 3, we have 3. Or we can write it as a sequence like this. We have 0 till 0 and then 1, 2, 3, etc. And this is obviously obtained by sampling the continuous time version of the signal r of t. Let us first understand its relationship with unit step sequence and unit impulse sequence. We can actually write r of n as u of n minus 1 plus u of n minus 2 plus u of n minus 3, etc. like that. How does this become r of n? Let us take different values for n first. So 0, 1, 2, 3, 4, and so on. So we know u of n minus 1 gives 1 for every value of n that is greater than 1. So we get 1 here, 1 here, 1 here, 1 here, and it goes on like that. U of n minus 2 gives 1 when n is greater than or equal to 2. So like this. U of n minus 3 gives from 3. Now you can see what is happening here. At n equal to 1, we have 1. At n equal to 2, we have 2. At n equal to 3, we have 3. At n equal to 4, we will have 4 when we consider u of n minus 4 as well. So that means when you add all of these sequences, you are actually getting r of n. We can write this as a summation as well, that r of n will be equal to summation from k equals 1 to infinity u of n minus k. If you want to start the summation from k equal to 0, then you can write it like this, or r of n is summation from k equal to 0 to infinity u of n minus k minus 1. Because when you give k equal to 0, we should get the first sequence, that is u of n minus 1. So you will get u of n minus 0 minus 1. So you will get that. You can also write it this way. R of n is summation from k equals minus infinity to n minus 1 of u of k. Let's try giving values. If you give the maximum value n minus 1 to k, you will get u of n minus 1. The next value that is below n minus 1 will be n minus 2. If you give that to k, you will get u of n minus 2. The next value n minus 3, you will get u of n minus 3. Goes on like that, and we are exactly getting this. So that is also a mathematical representation of r of n. So let's move on to its relationship with unit impulse sequence. It is even easier to write r of n in terms of impulse sequences. All you have to do is delta of n minus 1 plus 2 delta of n minus 2, 3 delta of n minus 3. It goes on like that. So at 1, we have one impulse of magnitude 1. At 2, we have one impulse of magnitude 2. At 3, we have one impulse of magnitude 3, which is basically the definition of R of n. So we can write R of n is equal to summation from k equals 1 to infinity delta of n minus k. Wait, we have to amplitude scale as well. So k delta of n minus k. You can try yourself to write other versions of the same summation as we have done over here. Let's move on to the first property, amplitude scaling. R of n gives n, so k r of n will give us kn if n is greater than or equal to 0, and still 0 when n is less than 0. We can take different cases. If k is greater than 1, every value will be multiplied by that number, so our graph will look like this. If k is between 0 and 1, the magnitude will again be scaled by k, so it will become lesser than what it was earlier. Our graph is going to look like this. Let us take the next case when k is less than minus 1. Every value will be multiplied with that number, so it will get reversed as well as multiplied. So the graph will look like this. In the last case, when k is between minus 1 and 0, the values will be reduced as well as reversed since it is negative. So the graph is going to look like this. The next property is time shifting. We know R of n has value 0 till 0. If I take R of n plus n naught, I'll have 0 until minus n naught instead of 0. If I take R of n minus n naught, I will have 0 until plus n naught. Let's write them mathematically. Since R of n is n, R of n plus n naught will be n plus n naught. When n is greater than minus n naught, it will be 0 as long as n is less than or equal to minus n naught. Similarly, R of n minus n naught will be equal to n minus n naught when n is greater than n naught, and it is 0 when n is less than or equal to n naught. The next property is time scaling. That is, we'll take some R of kn. There are different cases. Let's take when k is greater than 1 at first. For example, let's take R of 2n. At n equal to 0, I just get R of 0. At n equal to 1, I get R of 2. At n equal to 2, I get R of 4. When n is less than 0, I am getting 0 anyways. So the only thing that is happening is it is getting faster. R of 2 now doesn't come at 2, it already comes at 1. R of 4 doesn't come at 4 anymore, it is coming at 2 itself. So it's getting faster and our graph will look like this. Now let's take an example where 0 is less than k and it is less than 1. R of 0.5 n. At n equal to 0, I will get R of 0, which is 0. At n equal to 1, I will get R of 0.5. At n equal to 2, I get R of 1. So what is happening here is it is getting slower. R of 0.5 is supposed to come at 0.5, but now it is only coming at 1. R of 1 is now coming at 2. So our graph will look like this. The next case is when k is less than minus 1. As an example, I will take R of minus 2n. At n equal to 0, I will get R of 0, which is 0. If I take a positive value for n, like n equal to 1, I get R of minus 2. But we know R of minus 2 is 0. The same will be the case if you take n as any positive value, you will only get 0. Let's take n equals minus 1. Then I will get R of minus 2 into minus 1, 2. R of 2 is 2. Similarly, at n equals minus 2, I will get R of 4, which is 4. So two things are happening here. We're getting values only on the negative side, that is time reversal is happening, plus every value gets multiplied, so amplitude scaling is also happening. Our graph will look like this. The next case is when k is between minus 1 and 0. So k has a magnitude less than 1 and it is negative. Taking an example, r of minus 0.5 n. At n equal to 0, we get r of 0, which is 0. At n equals 1, we get r of minus 0.5, which is again 0. The same will be the case for every positive value of n. You will only get 0. Let's take n equals minus 1. Then it will be r of plus 0.5. At n equals minus 2, you will get r of 1. So this is time reversed and it has gotten slower. 0.5 is only now coming at minus 1. 1 is only coming at minus 2. So our graph will look like this. Let's write mathematical definition. For k greater than 0, r of kn will be kn if n is greater than or equal to 0 and 0 if n is less than 0. Similarly, for k less than 0, r of kn is going to be kn, but only if n is less than or equal to 0, and it will be 0 if n is greater than 0. The next property is time reversal, and it's pretty obvious. In r of n, we have 0 until 0, and then we get 1, 2, 3, etc. In r of minus 1, we have 0 for all the positive values including 0, and on the negative side of n, we have 1, 2, 3, etc. Mathematically, r of minus n will be minus n if n is less than or equal to 0, and 0 if n is greater than 0. Let us now solve a problem. We have to plot x of n, and x of n is r of n minus r of n minus 1. First, let's write r of n in the form of a sequence. So we'll have 0, 1, 2, 3, like that. And our zeroth term is 0. R of n minus 1 will be shifted 1 units towards the right. So the 0th point will be over here. Then we have another 0, 1, 2, 3, etc. What we have to find out is their difference. R of n minus r of n minus 1. We can just subtract the corresponding terms. 0 subtracted from 0, first term is 0. Actually, this is the 0th term. Then 1 minus 0, we get 1. 2 minus 1, again 1. Then 3 minus 2, 1. The next will be 4 minus 3, again 1. So you will just keep getting 1. On a graph, it will look like this. You can see one thing from the graph. This x of n is nothing but u of n minus 1. It is u of n that has been shifted 1 unit towards the right. So that's all about it. See you in the next video.